Wastewater treatment is a critical aspect of protecting public health and the environment. Untreated wastewater contains a variety of contaminants. These contaminants include pathogens, nutrients, and organic matter. Discharging untreated wastewater into the environment can lead to serious consequences. These consequences include waterborne diseases, oxygen depletion in water bodies, and harm to aquatic life. Effective wastewater treatment processes are essential to remove or break down these contaminants. Treatment plants are designed to mimic and accelerate natural purification processes. This ensures that the treated effluent meets regulatory standards. It also helps protect our precious water resources. Properly designed treatment plants safeguard public health. They help to prevent the spread of diseases like cholera and typhoid. By removing nutrients like nitrogen and phosphorus, treatment plants also protect our ecosystems. Excessive nutrients can lead to algal blooms. These blooms deplete oxygen in the water, harming fish and other aquatic life. Wastewater treatment is not just an environmental necessity, it's an investment in our future. By treating our wastewater effectively, we can ensure the availability of clean water for generations to come. Wastewater treatment systems vary widely in complexity and treatment levels. The choice of system depends on factors such as the characteristics of the wastewater, the desired effluent quality, and cost considerations. Primary treatment is the first stage in most wastewater treatment systems. It involves the physical removal of solids such as grit, sand, and large debris through processes like screening and sedimentation. Secondary treatment focuses on biological processes to degrade the remaining organic matter in the wastewater. This is often achieved through the use of activated sludge systems or trickling filters. Tertiary treatment, also known as advanced treatment, provides a higher level of purification. It targets specific contaminants that may not be fully removed by secondary treatment. Examples of tertiary treatment processes include filtration, disinfection, and nutrient removal. In addition to these conventional treatment systems, natural or nature-based systems are gaining popularity. These systems utilize natural processes and environments to treat wastewater. Examples include constructed wetlands and waste stabilization ponds. The selection of the most appropriate wastewater treatment system requires careful consideration of various factors. These include the volume and composition of the wastewater, treatment goals, land availability, and economic constraints. Waste stabilization ponds, also known as lagoons, offer a natural and cost-effective approach to wastewater treatment. These engineered systems utilize natural biological processes to treat wastewater. They are particularly well suited for areas with ample sunlight and land availability. Waste stabilization ponds consist of shallow earthen basins designed to hold wastewater for extended periods. During this time, natural processes, including algae growth and bacterial decomposition, work together to break down pollutants. Sunlight plays a crucial role in waste stabilization ponds by promoting the growth of algae. Algae produce oxygen through photosynthesis, which is essential for the bacteria that decompose organic matter in the wastewater. One of the significant advantages of waste stabilization ponds is their simplicity of operation and maintenance. They require minimal mechanical equipment and energy input compared to conventional treatment systems. This makes them a cost-effective option, especially for smaller communities or developing countries. Waste stabilization ponds are particularly effective in removing organic matter, pathogens, and nutrients from wastewater. The long retention times in the ponds allow for natural die-off of pathogens. The combination of sunlight, algae, and bacteria effectively breaks down organic pollutants. Nutrients, such as nitrogen and phosphorus, are assimilated by algae, preventing their release into the environment. Section 4. Classifying waste stabilization ponds. Waste stabilization ponds can be classified based on several factors, including the dominant biological reaction, discharge duration, extent of treatment, and cell arrangement. Based on biological reaction, aerobic ponds. These ponds are shallow, allowing sunlight to penetrate the entire water column. Oxygen is readily available throughout the pond, supporting aerobic bacteria that efficiently break down organic matter. Anaerobic ponds, deeper than aerobic ponds, anaerobic ponds have limited oxygen penetration. Anaerobic bacteria, which thrive in the absence of oxygen, are responsible for the decomposition of organic matter in these ponds. Facultative ponds. These ponds have both aerobic and anaerobic zones. The upper layers are aerobic, while the bottom layers are anaerobic. This combination of conditions allows for a wider range of biological reactions to occur, enhancing treatment efficiency. Based on discharge duration, intermittent discharge ponds. These ponds receive wastewater intermittently and are designed to store it for extended periods. Discharge typically occurs during the dry season or when storage capacity is reached. Continuous discharge ponds. As the name suggests, these ponds receive a continuous inflow of wastewater and discharge treated effluent at a steady rate, based on the extent of treatment. Primary ponds. These ponds provide primary treatment, primarily removing settleable solids and some organic matter. Secondary ponds. Secondary ponds provide a higher level of treatment, removing a significant portion of the remaining organic matter and pathogens. Tertiary ponds. These ponds are used for advanced treatment, targeting specific contaminants like nutrients or pathogens, based on cell arrangement as single-cell ponds. These ponds consist of a single basin where all treatment processes occur. Multiple cell ponds. These systems use a series of interconnected ponds, each designed for a specific stage of treatment. This arrangement allows for more efficient and controlled treatment. Section 5. Aerated lagoons enhancing wastewater treatment. While waste stabilization ponds offer a natural and cost-effective approach to wastewater treatment, they have limitations. One of the main limitations is their reliance on natural processes, which can be slow and less efficient than mechanical treatment methods. This is where aerated lagoons come in, offering a powerful way to enhance the performance of WSPs. Aerated lagoons are a type of wastewater treatment system that combines the benefits of natural biological processes with the efficiency of mechanical aeration. Like WSPs, they consist of shallow basins where wastewater is treated through a combination of algae growth and bacterial decomposition. However, aerated lagoons incorporate artificial aeration systems to provide a constant supply of oxygen to the water. The addition of aeration significantly enhances the treatment capacity of the lagoons. The increased oxygen levels promote the growth of aerobic bacteria, which are much more efficient at breaking down organic matter than anaerobic bacteria. This results in faster treatment times and improved effluent quality. Aerated lagoons are particularly effective in treating wastewater with high organic loads, such as those from food processing plants or industrial facilities. They can also be used to treat municipal wastewater, especially in situations where land is readily available and energy costs are relatively low.